For science class, let's go over chapter 16, the atmosphere. Weather and climate are two different things. Weather is what you're experiencing over a short period of time, and it's constantly changing. It's the reason why you can watch local news and they'll give you updates on chances of precipitation, daily highs and lows, incoming fronts. That's your weather, and that changes on an hourly basis. Climate is weather over long periods of time. It's generalized, it's composite. Essentially, when you start talking about what the average monthly temperatures in Central Florida are, that's when you're discussing climate, and that can change over long periods of time and over longer time scales, and has changed. Some of the elements of weather and climate are temperature, humidity, cloudiness, precipitation, air pressure, wind speed, and direction. And those are measured regularly with various instruments from a number of different governmental agencies, also institutions, research labs, and meteorologists at weather stations and all that. And our atmosphere is made up of mostly nitrogen, about 78%. The rest is oxygen, and at 21%. And argon and other gases make up about less than 1%. Carbon dioxide gets an honorable mention because of its effect on our climate. It only makes up 0.04% of our atmosphere in terms of composition. However, it exerts great control on our climate. So the atmosphere is just a discrete mix of gases, and here they are. There's a pie chart to show you that. Mostly nitrogen and oxygen, okay? Argon makes up about 1%, all others, this small little sliver here. And then this is carbon dioxide. Now it's past 400 ppm as of a few years ago. So there are other components to the atmosphere. There's water vapor, that's what the clouds are. About 4% of the air's volume is water in its vapor phase as it's kind of floating around in the atmosphere. And that's what forms clouds and precipitation. Water also absorbs a lot of heat energy from Earth. So it kind of regulates the heat radiating off the Earth's surface. There are also aerosols that are part of the atmosphere. Aerosols are tiny solid or liquid particles. Water vapor can condense on those solids, and what aerosols do is they reflect sunlight back into space. So they can actually lower global temperatures because it'll block out solar radiation. If you've ever noticed a pinkish sunrise or sunset, that color is due to aerosols. Aerosols can also be small particles from dust storms from deserts. This is the Gobi Desert, kicking up a bunch of the wind, picking up a bunch of fine silt into the air. And also volcanic eruptions can shoot up ash high up into the atmosphere. Those are considered aerosols as well. There's also an ozone layer in our atmosphere, and the ozone layer essentially is 3 oxygen atoms covalently bonded to one another. Okay, its distribution is not uniform, meaning that there's an area within the stratosphere where the ozone molecules are most concentrated, or are in highest concentration. And that's between 10 to 50 kilometers above the surface of the Earth. And what's great about ozone is it actually acts as a filter, and it absorbs a lot of UV radiation. And that's great, because UV radiation is It's not good for human cells or any living thing. It kind of alters gene expression and cause cancer. And so that's a great development in our atmosphere, and it's been there for a while. Human activity, some of the chemicals that we've synthesized, when released into the environment, break up this molecule. One example of this are chlorofluorocarbons, or CFCs. They're banned in the US now, not in every country, but what we realized is that this chemical was pervasive in the atmosphere when it was spilled. We used to use CFCs for refrigerants in refrigerators and air conditioning units, also in transformers. But once we realized that it breaks up the ozone molecule, and in fact there was a hole in the ozone layer, that's when politicians listened to scientists, and we had this manufacture of this chemical banned. And since then, the ozone layer has actually decreased since the ban. The hole itself has minimized. Okay, so here in 1979, this is the hole, or essentially an area of low ozone concentration. Okay, and then here, this is in 2012, so a well-defined hole over the southern pole. Since 2012, the ozone layer has been shrinking by a little bit, so it's kind of a success story. I mean, from here to here, obviously that's detrimental, but we got our act together since 2012, and the ozone layer hole is diminishing. The structure of the atmosphere changes from the surface of the Earth on towards when you exit the Earth and into space. What happens is pressure changes. What pressure is the weight of the air above you. Average sea level pressure is 14 pounds per square inch. And as you increase in altitude, pressure decreases. And so in Florida, we're essentially at sea level. Central Florida is anywhere between 40 and like 100 feet above sea level. So we're close to 1 atmosphere of pressure. When you go to areas of higher elevation, the pressure is reduced, and 1/2 of the atmosphere is below about 3.5 miles. All right, so here's an example. This is where we would be essentially, and then when you go up in elevation, the pressure is reduced. This is Mount Everest, and if you've ever seen any documentaries or witnessed any people climbing Mount Everest, you'll notice that they have oxygen masks once they get more than halfway up the mountain, and that's because 50% of the atmosphere lies below this line right here. So the majority of our atmosphere in terms of mass is down here. Okay, sorry for the mess. So once they get up to these areas, they have to breathe out of oxygen tanks because there's not enough oxygen in the atmosphere to support the climb, really, and that can have a lot of detrimental effects for climbers climbing Mount Everest. A lot of people die because of that lack of oxygen, and they start doing crazy things. Their brain swells, and yeah, it's a big mess. And that's why, like when you're flying on an airplane, the cabin's always pressurized, and if there's ever a hole or a door busts open, all the pressure in the cabin is higher, and so all the air kind of gets sucked out until it's equalized with the pressure of that altitude. So let's talk about the different layers of our atmosphere. The bottom layer is called the troposphere. That's the layer where we have most weather occur. Temperature decreases with altitude. We call this the environmental lapse rate. It's approximately every 1,000 feet in elevation you go up, the temperature decreases by 3.5 degrees Fahrenheit. The thickness varies, but on average is about 12 kilometers, and the upper portion of it is the tropopause. Now above the troposphere is the stratosphere. That goes from 12 kilometers to about 50 kilometers. And the temperature actually increases in the stratosphere. And that's why it kind of is defined as a new layer here. And within the stratosphere, you have the ozone layer. Then above the stratosphere, you have the mesosphere. That goes from 50 to 80 kilometers. And here the temperature starts to decrease again. And then lastly, you have the thermosphere, which has no well-defined upper limit because it just kind of fades into space, and really just a fraction of the atmosphere's mass. And here gases are moving at high speeds. There are a lot of collisions. This is where northern lights kind of show up at this level. We get auroras, okay, in the thermosphere. So if we start off in the troposphere, this is where we are. The temperature decreases in the troposphere as you go higher and higher to its edge. And this is where it ends, right at the tropopause. And that is a temperature of negative 70 degrees Fahrenheit. That's really cold. But what happens in the stratosphere is the temperature kind of levels off and then actually starts to increase. And the reason it increases is because of the incoming solar radiation. As it goes in through this layer of the atmosphere, the solar radiation or the UV radiation is being absorbed by the ozone layer. Now remember, there's ozone all over in the stratosphere. It's just most concentrated right around this area. And so that interaction generates heat, and because of that, the stratosphere heats up and you see a temperature increase right to the stratopause. Okay, it kind of gets down to about 0 degrees Celsius or 32 Fahrenheit at the stratopause. And then once you go beyond this, then the temperatures decrease to all the way to the mesopause, which is the border between the thermosphere and mesosphere, and those temperatures are really cold. That's a negative 90 Celsius or negative 130 Fahrenheit. So these are your layers, 1, 2, 3, 4 layers of our atmosphere. All right, let's talk about how the Earth and Sun move, or the Earth and Sun relation, orbital relation, or gravitational dance that they're in. The Earth rotates on its axis. It does a full rotation, 360 degrees in 24 hours. And it also revolves around the Sun. Okay, you can see that here. That's an elliptical orbit, so sometimes we're a little closer than the Sun and sometimes we're further away. All the while we're spinning every 24 hours as we're kind of orbiting the Sun in an elliptical form. But on top of that, if you notice down here, if you focus on this one, we have a tilted axis. So, oh God, that's supposed to be a circle. So the axis that goes through the center of our Earth is tilted about 23 degrees. Okay, and so what that does is that means that sometimes right here the northern hemisphere would be facing the Sun or tilting towards the Sun, and then like right here, and then the northern hemisphere would be tilted away from the Sun and its other part of its orbit, which means the northern hemisphere would be experiencing winter. And so that's why we have seasons. The reasons why we go from summer, winter, fall, at least in Florida, it's summer and light summer, but it's because of the changing sun angle and the result of this dip in our tilt. Okay. So what happens if we pretend we're in New York, for example, if we're in New York during the summer, June 21st to 22nd is the longest day of the year in the northern hemisphere. We call that the summer solstice. And if you were there, the sun angle would be 73.5 degrees during the summer solstice, almost directly above their head. It never really makes it kind of directly above your head. In Florida, it would be closer to like 90 degrees. The sun would be here during the summer solstice. So, but let's keep it in New York. When we go to the spring or fall, what will happen is there's a change in the angles sun in the sky. So it'll rise over here and then kind of not go up as high and then come back down. And so that angle is only about 50 degrees. In the summer, see the sun rises a little closer to the northeast and comes up higher in the sky and then comes out and sets closer to the northwest. And then in the wintertime, if you were living in New York, it's kind of sad. Look, the sun rises in the almost southeast, just barely makes it up over the horizon and then comes back down. So it's at a very shallow angle. It's about 26.5 degrees. And so what that means is during the wintertime, this is the winter solstice, the shortest day of the year, they receive the least amount of sunlight hours during the summer solstice. It's the shortest day or the longest night. Depending on where you live, at what latitude, and what season, the sun may be hitting you directly or indirectly. Okay, if you have the sun kind of directly above your head, like just 90 degrees, like you often do when you live in the tropics or close to the equator, that means that you have the most solar radiation in the smallest unit area. Okay, if you're somewhere else where the sun's coming in at an angle or the solar radiation's coming in at an angle, that means the same amount of solar radiation is spread over a longer distance. So if you're standing here, you're receiving less solar radiation per unit area than you would be if the sun was directly above your head. And again, if you have solar radiation coming in at a bigger angle, it kind of spreads even further. It's kind of like holding a flashlight directly pointing downwards on the floor. It'll form a perfect circle. That would be this example here. But if you start tilting that flashlight, more of that light is going to be spread across the floor. Okay, and that affects how much solar radiation these areas of Earth receive based on the sun angle. Okay. So the seasons, like we talked about, it's because our axis is tilted 23.5 degrees. So imagine we're rotating in a counterclockwise fashion, right? And if you're here, if you're in this portion of Earth, you're experiencing daytime, and as soon as you start rotating out of the face of the sun, you'll be rotating into darkness, and that's nighttime. Okay, so the axis is always pointed in the same direction. So sometimes when you're orbiting the sun, certain portions of the orbit, the axis will be pointing towards the sun, and sometimes it will be pointing away from the sun. Right? And then here are those sun's rays. Closer to the equator, do you see how direct that sunlight hits? So we get a lot more atmospheric heating in these areas because you get more direct solar radiation. As soon as you go to higher latitudes, you see how solar radiation comes in and spreads over a larger area. So when you're at higher latitudes, you receive less solar radiation and therefore less atmospheric heating. In addition to that, if you notice, at higher latitudes, the solar radiation passes through more atmosphere, and that increases the chances of atmospheric interactions, scattering, absorbing by clouds and stuff like that. So there's a few important days every year. The summer solstice, which we're approaching now, is on June 21st or 22nd. That's the longest day of the year. This is when in the northern hemisphere. Let me just repeat that, northern hemisphere. June 21st and 22nd in the southern hemisphere would be the winter solstice, their winter solstice. So this is when the sun's vertical rays are located directly at the Tropic of Cancer. Okay, so directly ahead. That's just a little south of us. And then the winter solstice, another important day. This is the shortest day of the year, and that's typically in December 21st or 22nd. And that's when the vertical rays are located on the Tropic of Capricorn, and that's in the southern hemisphere. All right, and Tropic of Cancer is in the northern hemisphere. All right, so it's the shortest day and longest day. And then there are equinoxes. These are pretty cool days. We have 2 of them a year, one in the autumn, typically September 22nd or 23rd, and in the spring, March 21st or 22nd. This is when the sun's rays, vertical rays, are located at the equator. And so what happens is the entire Earth experiences a day with 12 hours of daylight and 12 hours of nighttime everywhere, regardless of where you are. North Pole, South Pole, equator, Florida, New York, everyone receives 12 hours of daylight, 12 hours of nighttime. And that's because, let's see here, I guess it's not shown here. It'll be the next slide. So those are pretty important days. And here they are in terms of the orbit, okay? Here's the sun, obviously not to scale, but here's the equinox, okay? Well, it's hard to see here, but you have a fall equinox and a spring equinox, equal days all over the Earth, okay? Here's the summer solstice. If you notice, see how our tilt is pointing towards the sun? And then so just imagine the Earth rotating in this direction, okay? So that areas in the northern hemisphere are receiving a lot more sun than areas in the southern hemisphere. Notice that the majority of the southern hemisphere is in darkness. That's because they're experiencing winter. Whereas in the northern hemisphere, we're experiencing summer, very long summer days, lots of daylight. If you notice too, in certain areas, once you get closer to the poles, I want you to imagine this Earth spinning, and the portions of the northern hemisphere, as they spin, will not receive any night whatsoever. They're basically just facing the sun for an extended period of time. So if you go north of the Arctic Circle in the northern hemisphere summer, what you'll see is 24 hours of day, or what you'll experience is 24 hours of daylight. That sounds great, right? But you got to sleep sometime, right? So you have to have those like blackout windows and stuff. But what'll happen is like you'll see the sun rise, right? And then you'll have a full day, and then as the sun's going to set, it just starts to rise again. It just never goes away, and that's summertime in these really northern latitudes. The drawback is when the northern hemisphere is pointed away from the sun. Now imagine the Earth spinning this way. Do you notice that the northern north of 60 degrees latitude, it never actually faces the sun? So the flip side of it is in the wintertime, these areas experience 24 hours of darkness. And yeah, you think the quarantine's bad. Imagine never seeing the sun for an extended period of time, maybe like 2 or 3 months. It's depressing. Okay, so here's a more close-up view. So here in these areas during the summer solstice, they receive 24 hours of sunlight. If you go a little further south, this is more like New York. In the New York summer, you get 15 hours of sunlight. Here in Florida, we get about 13 and a half or 14 hours of sunlight during the summer. And if you live in the equator, there's no change whatsoever. So if you live in any of these areas here, every day is 12 hours of sunlight, 12 hours of nighttime, which is really cool and consistent. In addition to that, they don't really experience seasons. A lot of times if you live near the equator, it's just a rainy and a dry season is what they experience. They don't get fall or spring or winter. If you live in more or higher latitudes, okay, in the northern or southern hemisphere, then you'll see the greatest difference in daylight to nighttime hours, and also the greatest change in seasons, okay? And then here's what I'm talking about, the spring and autumn equinox. The light of illumination goes right through the axis of our planet. And so just imagine this rotating now counterclockwise. So this one special day, as it rotates, the entire Earth experiences 12 hours of daylight and 12 hours of nighttime. Perfect kind of night and day, 24-hour spin. It's pretty cool. Okay, let's talk about atmospheric heating. Heat is transferred from warmer to cooler objects. It's always transferred that way. And the way heat transfers, it does it in a couple different ways. One is conduction, so that's through molecular activity. That's like heating up your skillet to fry bacon or something. Your skillet will conduct the heat from your stove to the skillet. Convection is mass movement, so when you're boiling water, the water is actually moving. Okay, so it heats up at the bottom of the pot. Since it's hotter, it has lower density and it rises, then it cools and sinks and creates these circular motions. And then radiation is a type of heat transfer where you have electromagnetic radiation traveling through medium, like air or space, and it travels pretty fast in a vacuum. So here's your example. Here's radiation coming off of a fire. Okay. Here's heat transfer from the pot to this poor guy's hand. That's conduction. And then mass transfer, where you have convection currents. That's convection. So electromagnetic radiation consists of energy in a number of different wavelengths. Gamma rays are the highest energy and the shortest wavelength. Then there's X-rays, there's UV. The visible light is part of the electromagnetic spectrum. That's a portion of the magnetic spectrum that we can actually see, or that we can see. We've evolved an organ that can detect that portion of the electromagnetic spectrum. Infrared are longer wavelengths than visible. We can't see that, but we can feel that. That's heat. Okay, so like if you go out in the sun and the sunlight's hitting you, you'll start to feel warmer, and that's the infrared portion of the electromagnetic radiation. And then larger wavelengths are microwaves and radio waves. Let me show you a picture here. So here is the spectrum of visible light. Okay, even the individual colors have different wavelengths. So red has the largest wavelength, and violet and blue have the smallest wavelength. Okay. And then here are the gamma rays, the shorter wavelength radiation, and here's long wave radiation. So this is why we can see different colors through a rainbow as light is being diffracted through clouds and water vapor, and that kind of deflects or refracts the light and reveals white light in a bunch of different colors. So radiation is governed by a few basic laws. All objects, whatever their temperature, they emit radiation. Hotter objects radiate more total energy per unit area than cooler objects. The hotter the radiating body, the shorter the wavelength. And objects that are good absorbers of radiation also emit good radiation as well. So when the sun is it's a massive object, it's very bright, very hot, it's emitting a lot of electromagnetic radiation hurling towards us, in fact, in every direction. And so the atmosphere is largely transparent to that incoming radiation. But there are a lot of things that occur. There's reflection, we call that albedo, and we usually talk about it in terms of a percent. So we'll say, oh, the albedo is 10%. That means 10% of the incoming solar radiation is reflected directly back into space. Some of the solar radiation will scatter due to interaction with the atmosphere or clouds. Also, in some of that solar radiation will be completely absorbed by either clouds or molecules in the atmosphere. But most visible radiation does reach the surface of the Earth. And about 50% of that is absorbed at the Earth's surface. So let's take a look at what happens, or what's the fate of solar radiation as it kind of comes towards Earth, our atmosphere. So here it is. We start off with 100% solar radiation. 50% of that solar radiation is absorbed by land and sea. 30% is lost. 30% of this radiation is lost to space by reflecting. Okay, and 20 of that is reflected from clouds. 5 of that is backscattered by the atmosphere, and then 5 of that is reflected from sea and land. So that's what makes up that 30%. Okay, so we have 30, that's 80, and then the rest, 20%, is absorbed by atmosphere and the clouds themselves. All right, here are different surfaces that reflect solar radiation at different rates. Okay, if you have very thick clouds, you have 70 to 80% albedo. If you have thin clouds, only 25 to 30%. Snow albedo is really high. I don't know if you've ever been in snow, but you have to wear sunglasses, and you can get sunburnt from snow. At least I will. Very fair-skinned. But if you don't, like the sun will reflect off the snow like a mirror and then hit you in the face, and that can cause snow blindness. So the albedo of snow is really high. Areas that are darker or green have much lower albedo. okay, meaning they absorb more solar radiation. Okay, dark roofs, 10 to 15%. Water is highly variable, and it varies based on the angle of the sun. I don't know if you noticed this, but like early in the morning, say you're out in the water, right? Salt life, the sun will reflect off the water almost entirely, and it'll look like a mirror. But if the sun is way overhead, then there's very little albedo. Okay, so it just depends on the sun angle. So radiation comes off the surface of the Earth. So when solar radiation comes in and is absorbed by either land or sea, Earth re-radiates radiation outwards as well. Okay, we call this terrestrial radiation. And what happens is it comes out at longer wavelengths. So longer wavelength, or incoming is visible light, then is re-radiated out as infrared or as heat. So longer wavelength terrestrial radiation is absorbed by what we refer to as greenhouse gases, like carbon dioxide or water vapor. Okay, so here water vapor will absorb that long wave radiation and send it back towards the Earth's surface, like you see in this diagram. So here, that heating of our atmosphere is called the greenhouse effect. So let me show you 3 examples of this. I guess 3 planetary bodies that, well, the moon doesn't have an atmosphere. So when you have incoming solar radiation, it's shortwave radiation, and when that strikes the surface of the moon, then it's re-radiated out as long wave radiation, but there's no atmosphere to catch the infrared radiation, so that just goes back up into space. Okay. So that's why the surface of the moon, there's no trapped heat, and it's very cold. Okay, there could be no liquid water up here. It's too cold. On Earth, we've got like the Goldilocks situation, right, where we have an atmosphere, and incoming solar radiation comes in and strikes the Earth's surface, right? Then outgoing re-radiated heat or long wave radiation comes out, and a lot of it is trapped by some of the greenhouse gases. And remember, greenhouse gases like water vapor and carbon dioxide are necessary. If we didn't have any, we'd be like an ice house Earth covered in glaciers. We might have frozen oceans and stuff like that. But it helps regulate and absorb and keep a lot of heat on the Earth and allow us to have liquid water on the Earth's surface. However, there's a limit to this. There's a balance, right? We have to have a certain amount of carbon dioxide and other greenhouse gases within our atmosphere to kind of keep this stable. And so as that heat is absorbed by greenhouse gases, it's re-radiated back to Earth and keeps us kind of warm. But we can have a situation where we have a runaway greenhouse effect, and that's the case in Venus. Venus has an atmosphere that's almost entirely made up of greenhouse gases, mostly carbon dioxide. And so when incoming shortwave solar radiation comes in and strikes the surface of Venus, that's converted to long wave radiation, and it tries to escape, but then it's trapped by all the greenhouse gases, and that raises the surface temperature of Venus so high that it's about 523 degrees Celsius, or 941 degrees Fahrenheit. That's almost twice the broil setting in your oven. Okay, that cannot sustain life. Okay, that will melt metals at its surface. It's pretty crazy. So how do we measure temperature and talk about it and display it? Well, when you listen to the weather on the news or something, they'll give you a daily maximum or minimum. They'll also tell you daily mean, the range, monthly mean, annual mean, give you an annual temperature range. And oftentimes you'll see a map, and a map will be kind of shaded with all different colors. All those different colors represent isotherms, or different areas, or the borders between those colors are isotherms. Those are essentially just lines of connected points that are of equal temperature. Okay, so this is a map. So you would typically see this map right here, right? And then they'd give you assign a color and say this is 10 degrees, and anywhere in orange is between 80 and 89 degrees. All right, but in reality, what it is, these are those temperature isotherms. So along this line, any place in the US that is close to this line will have the same temperature of 80 degrees. Okay, and there are certain areas where the temperature gradient changes, right? So if you go, say you go from Houston all the way to Philadelphia. Okay, that's a pretty far distance. And what we see, we go from basically 80 degrees to about 60 degrees, and that's a pretty long distance. But if you go the same direction and the same distance from Houston to Missoula, let's say, maybe that's a little farther, what's happening here is you're crossing more of those isotherms, and the gradient is quicker. So it gets cooler faster as you go in, if you go in this direction. And so we call that a steeper gradient. So the temperature changes faster. So it goes 70, 60, 50, 40, 30, 20, and so forth. Okay. Well, what controls the temperature in different areas? Land and water, or proximity. If you're surrounded by land or surrounded by water, that helps adjust temperature. If you're landlocked or in the middle of the country, land heats up more rapidly and also cools down more rapidly than water. So it has a very, what it refers to, low specific heat. Okay, so in the summertime in the Midwest, it gets really hot. And in the wintertime in the Midwest, it gets really cold. So there's huge fluctuations of temperature if you're surrounded by land. If you're like Florida, which is surrounded by water on both sides, right, we're a peninsula, water has higher specific heat. What that means is that the amount of energy that's needed to raise the temperature of the water is much higher. So the oceans kind of regulate our temperature here. It doesn't allow us to go into like these wild swings of cold to hot. And that's why Florida weather is so great and consistent. Here's an example of differential heating off the coast of California. So here in this area, let's say during the day, the land will heat up so it's really hot. Here it's anywhere in red is in this area from 90 to like 113 degrees. Okay, so this area is really hot, but the water here remains pretty cold. It remains almost in the 30s. That's super cold. So there's a huge difference. The sun is hitting these two objects the same, yet the water remains really cold, and the land gets really hot, and that's because rocks and continental crust has very low specific heat. It heats up very quickly. Water, you need to use a lot of energy to change the temperature of water. In addition to that, water can mix really well, so it disperses heat really well and remains cool. And that has a great effect on your local climate. Let's compare two different cities, Vancouver and Winnipeg, and then you can choose where you'd like to live or where you prefer to live. This is mean monthly temperatures for two locations in Canada. All right, this is down here are the different months of the year, January to December. And then here are your temperatures, or average monthly temperatures in Fahrenheit or Celsius, whatever floats your boat. Okay, what if we notice is Winnipeg's in the middle of the North American continent, whereas Vancouver is near the ocean. Okay, so if you're surrounded by water, that has a positive kind of regulatory effect on temperatures. So Vancouver in the wintertime in January and in December is at an average temperature of 40 degrees. Okay. Winnipeg, on the other hand, its monthly average temperatures are down to about 10 degrees Fahrenheit, or a little lower there, 5 degrees Fahrenheit here, and that's because they're right there in the middle of the country. They're surrounded by land, and the air masses that sit over land will get very cold very rapidly because the land gets very cold very rapidly. Now let's compare their summertime. Summer, June, July, August. In Vancouver, the average temperatures during the summer, hottest portions of the summer, is about 65 degrees. Well, it's not a straight line. But in Winnipeg, it's almost 70. So Winnipeg gets hotter summers and colder winters. They have a much larger fluctuation in monthly average temperatures as compared to Vancouver, and that's because Vancouver is surrounded by water and Winnipeg is surrounded by land. In the summertime, the solar radiation strikes the land surrounding Winnipeg, heats up those air masses, and that keeps Winnipeg really warm. In the same token, in the summertime, the sun will hit the ocean water, but the ocean water temperature won't change that much, and so the air masses above them will remain mild and not too hot. So yeah, Vancouver is the place to live if you had a choice between Winnipeg and Vancouver. Now, altitude also controls your annual average temperature. Let's take Bolivia, for example. If we have, compare two cities, La Paz, which is like at really high altitudes in the Bolivian Andes, and Concepcion, which is close to the Amazon rainforest. Look at this. If you're in high altitudes, your average temperatures are in 40 degrees Fahrenheit in their summer, and then drops down to about lower 30s during their winter. Okay, and so they're at the same latitude, so it's apples to apples comparison. But Concepcion's at a much lower, they're like at sea level essentially, and their average temperatures are about 78 degrees during their summer and dips down to 75 during their winter. So Concepcion is much hotter throughout the entire year, and that's because they're at a lower elevation. When you're at high elevations, you have that cold air, cold mountain air that keeps your temperatures down. And then your geographic position, okay? A lot of people claim that the West has a much better weather than the East, and they're right. And that's because, say New York, let's take two cities, Eureka, California, and New York. Here the prevailing wind direction is this direction. These are the westerlies, okay? And so Eureka's on the windward side of the continent, meaning that the air masses typically move from over the ocean into California. And New York, since it's on the leeward side of the continent, the air masses move over the Midwest and through New York, okay? And so what happens there is, because the specific heat of water is higher, during the wintertime, the water temperature doesn't change that much, and so the air masses over the water are mild and then move over Eureka, and that's why Eureka has much warmer winters. See that? They're at an average of 50 degrees during the wintertime. Whereas New York is at an average of like 30 degrees during the winter, and the reason is because they have air masses that originate from the Midwest, and then they get really cold because they're over land, and the land's very cold, and then you get a very cold and harsh winter in New York. Okay. In the summertime, same thing happens. You get mild air masses move over the Pacific Ocean and into California, into Eureka, and the summers in Eureka are mild. They're cooler. The average temperatures are in the upper 50s. Whereas New York summers, they get really hot, and the reason is air masses from the Midwest that are hot because the land is heating up from all that solar radiation, heats up New York City. So again, live on the windward side of the coast. The East Coast, we have great weather. Pretty dry down here, and then really wet up here. So find your, see what you like. Okay, cloud cover and albedo affect daily temperatures. I don't know if you've noticed this, but in our winter times in Florida, say you have a really clear day, typically that's when a cold front kind of comes through and there are no clouds. Well, that day, the day will be much warmer because no clouds are blocking the incoming solar radiation. So if you're in the sun during the day, it's pretty hot. And then the overnight temperatures are really low. So the range during a clear day is really large. Okay, you have cold nights and warmer days. But if you had an overcast day, let me just erase that to avoid confusion. If you had an overcast day, the mornings will be much warmer, okay? And then during the day will be kind of, will be cooler. So the range is much lower. So what happens is clouds kind of minimize the temperature fluctuations during a day, because they kind of, during the hottest part of the day, they block the sun. And then overnight, the clouds kind of act as like a blanket and kind of warm it up a little bit. Okay, so our perception of temperature differs, right? Like people in California might be dealing with 90 degrees, but it's a dry heat. And so it's so dry you don't really sweat, or like if you do sweat, it evaporates so quickly, so you're just dry. But if you're in the summer in Florida, you know the humidity is going to be really high, pretty much saturated, and you're going to be soaked. You're going to be sweating like crazy. So they're really important factors. I mean, obviously air temperature, but relative humidity is really important. And that's what, here in Florida, we have a lot, really high relative humidity throughout the year, really. Wind speed's important. Places that, have kind of cold winters, like 30 degrees is not that cold, right? But if you have, 20-mile-an-hour winds, then all of a sudden it feels pretty cold. Okay, so that feels like temperature changes because of wind speed. And also sunshine. If you're in the shade, it might feel colder. If you're in the sun, it might feel hotter. All right, so those are all different factors. But the biggest controls on temperature variations on Earth are just essentially how much solar radiation is striking your portion of the Earth. Okay, and that's what really drives the temperature changes. So if we look at the world distribution of temperatures, we can draw isotherms across like different seasons on Earth and connect places of equal temperature just to see what like global temperatures are kind of like. So here's kind of an example of all the different isotherms that are forming and what you would see. Let me move on to the next global patterns. But what we see is temperature decreases towards the poles from the tropics. And that makes sense, obviously, because the tropics receive more solar radiation, more direct solar radiation. The poles receive more indirect solar radiation. Okay. And the warmest and coldest temperatures on Earth occur over land. And that makes sense, too, because the specific heat of land is so low. So they have huge fluctuations. In the summer, in the southern hemisphere, the isotherms are straighter, and that's because most of the southern hemisphere is water, so they're a little more stable. And annual temperature ranges are the smallest near the equator and increase with latitude, and that's because of our tilted axis and the seasons. Okay, and the greatest change in annual temperature occur over continents. So here you can see that. Look at the gradient if you go from and comparing like Southeast Asia towards Russia. Look how quickly that temperature changes so fast. You're going through a lot of isotherms. You're going from 60 degrees Fahrenheit all the way to -10, -20, -40, Siberia. My goodness. Okay, so what you see here is the winter time in northern hemisphere, and you see huge temperature gradients here, or quick ones. If you notice over the water, because of water-specific heat, the temperature gradients are spaced out. Okay, so that's a low gradient. If you look at the southern hemisphere, yeah, a lot of heat in this area. That's during their summer, so these areas get really hot, especially here in Australia. But if you go to the southern hemisphere, again, these are spaced out isotherms because it's mostly water down here. All right, if we compare July or northern hemisphere summer, yeah, that's us. We're in the red. Yeah, so we're experiencing it's really hot. And if you notice, the isotherms are really spaced out here. And then you see really quick gradients once you get onto land in the southern hemisphere, because that's Antarctica. But they're kind of spaced out over the water. All right, and then here's all that really hot northern hemisphere summer weather across the Arabian Peninsula, northern Africa, and into Asia.